Hello, my name is Brandon Wilson, the project manager of Cal State LA's Cryo-UAV Team, advised by Dr. Charles Hayes. We here at Cal State LA wish to illustrate our proof of concept for a manner in which the Artemis mission can harness robotic swarming technology for in-situ resource utilization for the sake of a sustainable lunar presence. This video will serve as an in-depth technical evaluation of our as-built Cryo-UAV stand-ins. Before the technical evaluation, some exposition. Through the introduction of cryogenically resistant unmanned aerial vehicles, hereto referred to as Cryo-UAVs, to the permanently shaded regions of the Moon, we would be able to detect water ice expected to be present on and in the lunar surface for its various applications to the Artemis mission, such as securing an in-situ water supply for the human landing system that will be housing astronauts both during transit and after arrival. Due to the expected depth of lunar water ice ranging from tens of centimeters to many meters, this substance's detection would be accomplished through the introduction of a terrain penetrator to the lunar surface, causing a forceful but controlled displacement of the regolith. Swiftly, the Cryo-UAV swarm would use mounted spectroscopy instruments in search of proof of water molecules, while also mapping the newly forged terrain. Once proof is established, proper excavatory robotics would be signaled by the swarm to quickly approach, using the mapping developed by the Cryo-UAV swarm for a safe and efficient descent. The use of expendable robotics as opposed to on-site astronauts in this scenario is both for convenience and to maintain a safe distance from the explosion and debris. With swarming, water ice detection can continue uninterrupted even if members of the Cryo-UAV swarm are put out of commission while in action, as there would be multiple other instrumented drones active. These Cryo-UAVs would be propelled by a hydro-LOX mixture and refueled from either astronaut wastewater electrolysis or, if the detection and excavation of lunar water ice is successful and sustainable, water ice electrolysis. To communicate this concept, we will be using Telo-EDU drones and a RoboMaster TT drone, along with an instrument suite equipped with LiDAR, IR sensing, GPS, IMU, and front-facing camera, or NavCam. First, we'll discuss the evolution of hardware, how the drone's externally mounted assembly changed with time to suit our needs. We'll then demonstrate the current progress with object detection and avoidance, followed by current progress on swarming, and ending with a discussion on measures made and experiments held for instrument verification. Throughout the past year of the project, we've sought to modify our commercial off-the-shelf device to suit our needs of in-flight data acquisition. At first, we had a Telo-EDU as it came, internal IMU, front-facing camera, and control through Wi-Fi connection. We purchased the DJI RoboMaster TT expansion kit, which enabled us to build instrument mounts on top of the drone using the kit's 2x3 Lego stud array. We experimented with a few designs before sticking with this model, with the TF Luna LiDAR, ESP32, and Raspberry Pi Pico W attached to have a more accurate total mass. Flight tests were successfully performed, demonstrating that the drone could handle both the added mass and the adjustment in center of mass. At this point, the problem of powering the RPi Pico W mid-flight presented itself. We had to choose between using the ESP32 that came with the expansion kit or the drone's internal battery to power the microcontroller. Without powering the RPi Pico W, no instrument data could be transferred between the mounted instrument and the base computer. We decided on drawing from the drone's power supply using a modified micro USB, where we've soldered its ID and ground pins together to configure the host drone into powering the RPi Pico W. After securing the micro USB's cable with string, equipping the LiDAR device with a screwed-on 3D printed backing, and taping down the wiring between the LiDAR and the Pico with Kapton tape, we are left with our current configuration for the mounting of instruments with the drone powering the Pico, enabling in-flight data acquisition. Equipping a drone with our IR camera would be as simple as purchasing another upgrade kit, copying the wiring and Lego assembly, 3D printing a new backing, and placing our IR camera where the LiDAR device is attached. As discussed in the systems engineering paper, Python object detection has been verified functional using OpenCV camera operation and TensorFlow model training, with datasets we made for rocks, puzzle pieces, and ice cube detection. Here is one of our Telo-EDU drones detecting rocks within our regolith simulant yard using its front-facing navcam. You've surely noticed that the program only seems to notice 3 rocks out of what appears to be about 100. The drone's relatively low processing power is a technical limitation that causes us to use TensorFlow Lite, a program that intentionally only visualizes the detection of 3 objects at once to conserve memory, even if more objects have been detected. With live navcam object detection achieved, autonomous decision-making based on object detection, i.e. object avoidance, is the next step for this element of the project. We can also consider ways to optimize our object detection code, allowing for a higher quality feed. Packet sender Python swarming code has been developed and proven functional for non-autonomous swarming between RoboMaster TT drone, Telo-EDU drones, and Freenove hexapod, and that hard-coded directions can be given to all devices to follow without delay. This is done through putting the drones and hexapods' IPs and port numbers into Packet Sender and allowing a nearby router to send commands between all connected vehicles. Our next step with Packet Sender Python swarming would be to implement decision-making based on readings from onboard instruments. For example, an experiment testing the efficiency of swarming once decision-making of this nature is implemented would be to see if a swarm of drones can locate a bucket of dry ice hidden within the enclosure using IR sensing and report its location to the hexapod, while also informing the hexapod of any obstacles in its path using LiDAR mapping. MATLAB swarming has been developed and proven functional for non-autonomous swarming between RoboMaster TT and Telo-EDU drones through the MATLAB support package for Rise Telo drones. However, as discussed in the systems engineering paper, an unavoidable 4-second delay between this package's functions makes drone motion using MATLAB swarming a fairly slow process. When you consider the speed necessary to analyze the displaced regolith discussed in the exposition and conceptual mission section of this video, it becomes evident why MATLAB as a platform for swarming has been retired. Our choice to use the TF Luna LiDAR as a remote distancing instrument came from trade studies performed during last year's NASA Mines competition. This year, to suit our needs, this instrument needed to be verified functional in at least one dimension while submerged in darkness. Our experiment to verify this involved placing the TF Luna LiDAR against the wall of a darkened 25-foot-long corridor and taking a distance measurement every 20 inches by holding still and then moving a poster board. Remote distancing data obtained from the LiDAR was sent from an attached Raspberry Pi PicoW microcontroller to a laptop computer via a Wi-Fi connection. This experimental data gathered verified TF Luna LiDAR functionality in darkness in one dimension within 25 feet. The error seen on the table can be accounted for through human error and imperfect placement of the poster board. Next, we need to verify our IR camera could function both for accurate remote thermometry and for thermal mapping. Our tabletop experiment for this verification had the following procedure. 1. Prepare water ice/regolith simulant in insulating dish and let the mixture equilibrate to 0 degrees Celsius. 2. Record water ice/regolith simulant surface temperatures using handheld infrared thermal sensor as a calibration. Here we have the dish's exterior, the dish's interior, a stray ice cube, and the equilibrated water ice/regolith simulant mixture. 3. Record water ice/regolith simulant surface temperatures using our IR camera instrument. Here we used an MLX 90640 high-resolution thermal camera, which outputs a 24 by 32 live thermal feed. The IR camera's data was taken using a Raspberry Pi PicoW microcontroller interfaced to a laptop computer, similar to the TF Luna LiDAR experiment's interface. As seen on the screen, the IR camera instrument accurately portrays the range of temperatures present and expected in the regolith simulant through the live camera feed. This is verification that the thermal mapping and accurate remote thermometry is achievable through this instrument. Our ATGM336H GPS model was chosen through trade studies performed during last year's NASA Mines competition. This year, we sought to verify that it could output accurate positional data. Unfortunately, the device refused to output any data whatsoever, reflected in the strings of asterisks where coordinates and other values should be. If all columns returned a value as opposed to a string of asterisks, the sentences RX check would return a 1. If all of the coordinates are correct by the module's standards, checksum fail would also return a 1, indicating usable data. This will require either further troubleshooting or a replacement of the GPS model.